In the vast cosmos, the James Webb Space Telescope, JWST, symbolizes human ambition. Launched on December 25, 2021, after decades of development and a $10 billion budget, it is redefining our understanding of the universe. Most people don't look up anymore. They scroll past the sky, past the mystery, past everything that reminds them they're small. But you stopped here. You're one of the few still searching for something real. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Its 6.5-meter gold-coated mirror and infrared sensors detect light from the earliest stars and galaxies, reshaping astrophysical history. JWST's first. Images unveiled galaxies so ancient their light travelled over 13.5 billion years. These mature systems with spiral arms and glowing cores suggest a thriving universe just 200 million years after the Big Bang, challenging cosmic evolution timelines. Nearby, JWST studied LHS 475b, a rocky exoplanet 41 light-years away. Its carbon dioxide-rich atmosphere hints at a complex geological past, but its surface temperature tests habitability theories. Pushing planetary science boundaries, JWST's spectrographs have detected mysterious signals in distant star spectra, suggesting unknown elements or compounds. Once a fringe endeavour, the search for extraterrestrial intelligence, SETI, is gaining traction as JWST's findings raise serious questions about the origins of these signals. Observation, interpretation, speculation. JWST's data has sparked debates among astrophysicists. Do these ancient galaxies imply faster cosmic formation or flaws in current models? Could exoplanets like LHS 475b support life adapted to extremes? And what of the strange stellar signals? Are they evidence of new physics or signs of advanced civilizations? As scientists explore these questions, JWST continues its cosmic survey. Each discovery is a step into the unknown, revealing a universe stranger and more wondrous than imagined. The cosmos, once unknowable, is becoming a tapestry of stories, each a tribute to human curiosity. Part 1. The Awakening. What if the universe is not the chaotic, random expanse we've always believed it to be? What if, instead, it is a place of order, symmetry, and deliberate design? The James Webb Space Telescope, launched on December 25, 2021, after decades of development and over $10 billion in investment, has begun to unravel this question. With its 6.5-meter-wide gold-coated mirror, composed of 18 hexagonal segments, and state-of-the-art infrared detectors, it has started to reveal patterns and structures that defy our most fundamental models of astrophysics. In the galaxy cluster Abell 2744, located some 3.5 billion light-years away, researchers found perfectly aligned light points, symmetrical structures forming patterns that should not exist in the chaotic world of galactic evolution. These formations stretch across billions of light-years, repeating with geometric precision that seems almost intentional. Imagine staring into the depths of space, where light itself has journeyed for eons to reach our telescopes. Abell 2744, also known as Pandora's cluster, is a colossal cosmic collision, a merger of at least 4 smaller galaxy clusters. It is a place where galaxies are torn apart and reassembled by gravity, where superheated gas glows with the intensity of 1 billion suns. Yet within this seemingly chaotic region, Webb's infrared eyes have detected. Order. Stars and galaxies align in ways that defy simulation, forming geometric shapes that echo across the void. The probability of such patterns emerging randomly is astronomically low, less than 1 in a trillion, challenging the very foundations of our understanding of the cosmos. The cluster's total mass, including dark matter, is estimated to be around 4 trillion solar masses, making it one of the most massive structures in the observable universe. Observations. The James Webb Space Telescope has captured detailed images of galaxy clusters, spiral galaxies, and exoplanets, revealing anomalies that contradict established theories. In the galaxy cluster SMACS 0723, for instance, Webb's first deep-field image unveiled thousands of galaxies in a region of sky no larger than a grain of sand held at arm's length. Among these galaxies, some appear distorted, stretched, and magnified by the gravitational lensing effect of the cluster's immense mass. Yet, within this distortion, there are symmetries that defy explanation. Galaxies curve around invisible arcs, as if tracing the contours of an unseen hand. The deep-field image revealed galaxies as they appeared 13.1 billion years ago, just 700 million years after the Big Bang, offering a glimpse into the universe's infancy. In the Cartwheel Galaxy, located 500 million light-years away in the constellation Sculptor, Webb's observations have revealed unprecedented detail. This galaxy, shaped like a wagon wheel with a bright inner ring and a surrounding outer ring, is the result of a high-speed collision between a large spiral galaxy and a smaller intruder. Yet the symmetry of its structure is breathtaking. The outer ring, glowing with the birth of new stars, is almost perfectly circular, despite the violence of its origin. The spokes connecting the inner and outer rings are evenly spaced, like the strands of a spider's web. The Cartwheel Galaxy spans about 150,000 light-years across, making it one of the largest known spiral galaxies. Interpretation. These patterns could be the result of gravitational interactions over billions of years, or they could hint at a deeper symmetry embedded in spacetime itself. The theories of general relativity and quantum mechanics describe a universe where randomness and order coexist in a delicate balance. Yet, the patterns observed by Webb seem to tilt this balance toward order. They suggest a cosmic framework where forces and interactions are more finely tuned than we ever imagined. Could there be a hidden variable, a missing piece in our equations that explains these symmetries? The concept of fine-tuning in the universe has been a subject of debate among physicists, with some arguing that the precise values of fundamental constants are not random, but rather the result of an underlying structure. In the Stephan's Quintet, a compact group of galaxies 290 million light-years away, Webb has observed interactions that defy conventional explanations. The galaxies dance around each other, their gravitational forces intertwining in a cosmic waltz. Yet, within this dance, there are patterns that seem almost choreographed. Stars align in straight lines. Galaxies rotate in synchrony, and gas clouds form geometric shapes that should not exist in such a dynamic environment. These observations hint at a deeper symmetry, a cosmic harmony that underpins the universe. The galaxies in Stephan's Quintet are so close that they are gravitationally bound, meaning they will eventually merge into a single, massive galaxy. Speculation. What if these formations are not random, but are evidence of a cosmic order? We have yet to understand. Are we witnessing the fingerprints of a universe that remembers its past? The idea of a memory of the universe is not new. It has been proposed in various forms, from the concept of cosmic inflation to the holographic principle. Yet, Webb's observations add a new dimension to this idea. They suggest that the universe not only remembers its past, but also encodes it in the very fabric of space-time. The holographic principle, for instance, posits that all the information contained in a volume of space can be represented as information on the boundary of that space, much like a two-dimensional hologram. The anomalies don't stop there. In NGC 1365, a spiral galaxy 60 million light-years away, unusual motion patterns suggest gravitational behavior that defies our most basic models. This galaxy, part of the Fornax cluster, is known for its active galactic nucleus, a supermassive black hole that feeds on surrounding gas and stars. Yet, Webb's observations have revealed that the stars and gas in NGC 1365 move in ways that contradict our understanding of gravity. They orbit the black hole in perfect synchrony, as if guided by an unseen hand. The black hole at the center of NGC 1365 is estimated to be about 2 million solar masses, yet its influence seems to extend far beyond what current models predict. These discoveries are not isolated incidents. They are part of a larger tapestry of cosmic mysteries that the James Webb Space Telescope is unraveling. In the Southern Ring Nebula, a planetary nebula 2,500 light-years away, Webb has observed intricate patterns in the gas and dust expelled by a dying star. These patterns, which resemble the petals of a cosmic flower, defy explanation. They suggest a level of order and symmetry that should not exist in such a turbulent environment. The Southern Ring Nebula is approximately 0.5 light-years in diameter, yet its complex structures are visible in stunning detail thanks to Webb's advanced optics. As we peer deeper into the universe, the questions grow louder. Are these patterns mere coincidences, or are they evidence of a cosmic order we have yet to comprehend? The James Webb Space Telescope, with its unparalleled sensitivity and resolution, is our best hope of finding answers. It is a tool that allows us to see the universe as it truly is, not as we imagine it to be. And what it reveals is a cosmos of breathtaking beauty and profound mystery, a place where order and chaos, symmetry and randomness coexist in a delicate balance. The telescope's primary mirror, made of beryllium coated with a thin layer of gold, is designed to capture infrared light with unprecedented clarity, enabling scientists to study distant galaxies, stars, and exoplanets in ways never before possible. Imagine the vast expanse of the cosmos, stretching across 93 billion light-years, filled with over 100 billion galaxies, each containing hundreds of billions of stars. The James Webb Space Telescope, positioned at the Lagrange point L2, 1.5 million kilometers from Earth, provides an unobstructed view of this cosmic tapestry. Its observations have already challenged our understanding of dark matter, the invisible substance that makes up approximately 27% of the universe. In the Bullet Cluster, a merger of two galaxy clusters, Webb's infrared eyes have detected the separation of dark matter from normal matter, hinting at a hidden structure that governs the distribution of this elusive substance. The telescope's observations have also shed light on the mysterious nature of dark energy, the enigmatic force responsible for the accelerating expansion of the universe. By studying distant supernovae and the large-scale structure of the cosmos, Webb has provided new insights into the nature of this cosmic repulsive force, which makes up about 68% of the universe. The telescope's ability to peer into the distant past, to the epoch of reionization has allowed scientists to study the formation of the first stars and galaxies, offering clues to the universe's earliest moments as we delve deeper into the cosmic mysteries revealed by the James Webb Space Telescope. We are forced to confront the limitations of our current understanding. The patterns and symmetries observed in the universe suggest a level of order that defies our most advanced theories. They hint at a cosmic framework where forces and interactions are more finely tuned than we ever imagined, challenging us to rethink our place in the universe and the nature of reality itself. The telescope's ongoing mission promises to unveil even more profound discoveries, pushing the boundaries of our knowledge and inspiring future generations to explore the cosmos with renewed wonder and curiosity. What we know versus what we don't know. The James Webb Space Telescope has captured detailed images revealing anomalies in galaxy clusters and spiral galaxies. It has observed symmetrical patterns in Abell 2744, unusual motion in NGC 1365, and geometric structures in the Cartwheel Galaxy. These observations challenge our understanding of the universe and hint at a deeper cosmic order. The telescope's advanced infrared detectors have allowed scientists to study the composition of exoplanet atmospheres, revealing the presence of water vapor, methane, and other molecules that could indicate the potential for life beyond Earth. Unknown whether these patterns are the result of random gravitational interactions or evidence of a deeper cosmic order. The mechanisms behind these symmetries remain a mystery, as do the implications for our understanding of the universe. Are we witnessing the fingerprints of a cosmic design, or are these patterns the result of forces and interactions we have yet to comprehend? The James Webb Space Telescope continues its mission, peering deeper into the cosmos, seeking answers to these profound questions. Its ongoing observations of distant galaxies, quasars, and the cosmic microwave background radiation promise to shed light on the universe's earliest moments and the fundamental laws that govern its evolution. The telescope's ability to detect and study exoplanets in unprecedented detail offers the tantalizing possibility of discovering life beyond our solar system, forever changing our understanding of the cosmos and our place within it. Part 2. The Impossible Planet. What if a planet existed that defied every law of planetary formation? HIP 6E6b, an exoplanet located hundreds of light-years away, is just such a world. 7 times the mass of Jupiter, it orbits its star at 3 times the distance of Neptune, a configuration that should be impossible. The star itself is barely 15 million years old, a cosmic infant in the grand timeline of the universe. Yet this planet exists, stable and glowing at over 1,000 degrees Kelvin, in a system that shouldn't have had time to build it. This is not merely a puzzle, it is a direct contradiction to the core principles of planetary formation, a field of study built on centuries of observation and theory. Every known planet, from the rocky inner worlds of our solar system to the gas giants and icy bodies beyond, follows a predictable pattern of formation. Yet HIP 6E6b stands alone, a cosmic outlier that challenges the very foundations of astrophysics. The young star, HIP 6E6, is a fiery adolescent, its surface seething with magnetic storms and solar flares. At this stage in its life, it should still be surrounded by a swirling disk of gas and dust, the raw materials from which planets are born. Yet, there is no disk. The region where HIP 6E6b orbits is eerily empty, as if the planet materialized fully formed, bypassing the slow, chaotic process of accretion that birthed every other known planet. Its temperature, over 1,000 degrees Kelvin, is another anomaly. While most exoplanets cool gradually over billions of years, HIP 6E6b remains inexplicably hot, hinting at an internal heat source or an unknown mechanism that defies our understanding of thermal dynamics in space. This heat could be the result of ongoing geological activity, such as intense volcanism or tectonic processes, but the data so far offers no clear explanation. Observations. HIP 6E6b is a massive exoplanet orbiting a young star, defying current theories of planetary formation. Its mass, temperature, and orbital distance are inconsistent with the age of its parent star. The absence of a protoplanetary disk or debris field suggests it did not form through traditional accretion processes. The planet's stable orbit and thermal properties imply an origin story that predates its current star system, raising. Questions about the life cycle of stars and planets in the cosmos. Interpretation. The planet's existence challenges our understanding of how planets form and evolve. Its temperature and lack of a protoplanetary disk suggest it may have formed elsewhere, or under conditions vastly different from those in its current system. The stability of its orbit further complicates the picture, as any disruption in its formation or migration should have left. Visible traces, such as a scattered debris field or gravitational perturbations in the system. The absence of these features deepens the mystery. Speculation. Could HIP 6E6b be a relic from a previous star system, deliberately placed or transplanted by an unknown force? Or is it the product of a rare, undiscovered astrophysical phenomenon that rewrites the rules of planetary formation? The idea of a planet being moved from one star system to another seems far-fetched, but the laws of physics do not preclude the possibility. Gravitational interactions, though rare, can eject planets from their orbits, and under certain conditions these planets could potentially be captured by another star. However, the precise mechanics of such an event remain purely theoretical. The absence of a visible protoplanetary disk or leftover material only deepens the mystery. Some researchers speculate that this planet is not a product of its current system at all, but a remnant of a previous cycle, a relic from a star system that came before. This hypothesis, while extraordinary, is not entirely without precedent. In recent years, astronomers have discovered rogue planets, worlds wandering the cosmos without a star to call their own. These planets, ejected from their original systems through gravitational interactions, raise the possibility that planets can survive the death of their parent stars and potentially be recaptured by new ones. If HIP 6E6b is such a relic, it would redefine our understanding of planetary migration and the life cycle of star systems. However, the idea of a planet being transplanted into a new system is purely speculative. The logistics of such an event are mind-boggling. A planet like HIP 6E6b, with its immense mass and gravitational pull, would require an external force. Capable of precision on a cosmic scale, this force would need to navigate the delicate balance of velocities, trajectories, and gravitational influences to insert the planet into its current orbit without destabilizing the system. The energy required for such an operation is almost unfathomable, dwarfing the output of even the most powerful stars. To put it into perspective, the total energy released by the Sun over its 4.6 billion year lifespan is estimated at around 1044 joules. The energy needed to move a planet like HIP 6E6b could be orders of magnitude greater, pushing the boundaries of what is theoretically possible. If HIP 6E6b is indeed a relic, it suggests a universe with a history far older and more complex than we ever imagined. It implies that stars and planets are not isolated, one-time creations, but part of an ongoing cycle of birth, death, and rebirth, this idea challenges our linear view of cosmic evolution, hinting at a universe where time and causality are not as straightforward as they seem. It also raises profound questions about the nature of existence itself. If planets can outlive their stars and migrate across the cosmos, then the very concept of a home system becomes fluid, and the boundaries between star systems blur into a web of interconnected histories. To better understand HIP 6E6b, astronomers have turned to advanced telescopes like the James Webb Space Telescope, JWST. Launched in 2021, the JWST is equipped with instruments capable of studying exoplanets in unprecedented detail. Its infrared capabilities allow it to peer through the dust and gas that obscure many star systems, providing clearer images and more accurate measurements of distant worlds. By analyzing the light emitted and reflected by HIP 6E6b, scientists hope to uncover clues about its composition, atmosphere, and potential origin. The JWST's spectrographs can identify specific chemical signatures in the planet's atmosphere, such as carbon dioxide, methane, or even complex organic molecules, offering insights into its past and present conditions. One key observation involves the planet's thermal signature. The JWST can measure the heat emanating from HIP 6E6b with exceptional precision, helping researchers determine whether its internal heat is the result of ongoing geological activity or an unknown energy source. Additionally, the telescope can detect the presence of specific molecules in the planet's atmosphere, such as water vapor, methane, or even more exotic compounds. These molecules could provide insights into the planet's history, revealing whether it formed in its current location or was transplanted from elsewhere. For example, the presence of heavy isotopes like deuterium could suggest that the planet formed in a colder, denser region of the cosmos far from its current star. Another avenue of investigation is the planet's magnetic field. Planets with strong magnetic fields like Earth and Jupiter are often shielded from solar radiation and cosmic rays, allowing life to flourish. By studying HIP 6E6b's magnetic field, scientists can learn more about its internal structure and whether it has the potential to support life, or if it ever did in the past. The presence of a magnetic field could also hint at the planet's origin. For instance, a particularly strong field might indicate a rapid formation process or an unusually dense core, both of which could challenge existing theories of planetary formation. What we know versus what we don't. Known, HIP 6E6b is a massive, stable exoplanet orbiting a young star. It has a temperature of over 1000 degrees Kelvin and no visible protoplanetary disk. Its existence challenges current theories of planetary formation. Its orbit is stable and its thermal signature suggests an internal heat source, though the nature of this source remains unclear. Unknown. How the planet formed and whether it is a relic from a previous star system. The source of its internal heat and the composition of its atmosphere remain mysteries. The possibility of a magnetic field and its implications for the planet's history are still under investigation. The precise mechanisms that allowed HIP 6E6b to achieve its current orbit without destabilizing the system are also unknown. As researchers continue to gather data, HIP 6E6b remains a symbol of the unknown, a reminder that the universe is far stranger and more wondrous than we can ever fully comprehend. Its story is one of cosmic riddles and profound questions, testament to the endless frontier of human curiosity. In the vast expanse of the cosmos, HIP 6E6b stands as a beacon of mystery, a world that defies explanation and invites us to rethink our place in the universe. Part 3. The Perfect Ring. What if the universe held symmetries so precise that they defied the laws of probability? The James Webb Space Telescope, a marvel of modern engineering with its 6.5-meter gold-coated mirror and sensitivity to infrared light, has captured an image that challenges our understanding of the cosmos. This image showcases an Einstein ring, a gravitational lens caused by a massive foreground galaxy bending the light of one directly behind it. But this ring, located around galaxy J418, is unlike any other. It is nearly perfect, a full uninterrupted circle of light with mathematical symmetry that stuns even the most experienced astrophysicists. The ring's diameter spans approximately 100,000 light-years, a scale so vast it is difficult to comprehend. The Einstein ring glows faintly in the infrared spectrum, its light having travelled for over 9 billion years before reaching the telescope's mirrors. This is not just a distant observation, but a glimpse into the early universe, a time when the cosmos was less than half its current age. The Einstein ring around galaxy J418 is not just a curiosity, it is a gravitational lens with near-perfect symmetry, a phenomenon that has astrophysicists re-evaluating their models. The light from the background galaxy, magnified and warped by the foreground galaxy's gravity, travels billions of light-years to reach us. This journey is not a straightforward path, but a dance through the fabric of space-time, influenced by the immense gravitational forces at play. The precision of this alignment is akin to threading a cosmic needle, an event so rare it defies statistical probability. Imagine a beam of light, delicate and precise, curving gracefully around the immense gravitational well of the foreground galaxy, its path dictated by the unseen forces of dark. Matter and the black hole at the galaxy's core, the result is a ring so perfect it seems almost artificial, a cosmic masterpiece painted across the void of space. Observations. The Einstein ring around galaxy J418 is a gravitational lens with near-perfect symmetry. The light from the background galaxy is bent into a flawless circle, a sight that has never been observed with such precision. The foreground galaxy, J418, is a massive elliptical galaxy, with a central black hole estimated to be billions of times the mass of our Sun. This black hole's gravitational pull is the primary force shaping the Einstein ring into its perfect form. Its mass is so immense that it warps space-time itself, creating a lens that magnifies the light of the distant galaxy behind it. The background galaxy, though obscured by the brilliance of J418, is believed to be a spiral galaxy, its structure distorted and stretched by the gravitational lensing effect. Interpretation. Such symmetry requires an exact alignment between the two galaxies down to fractions of a degree across billions of light-years. To put this into perspective, imagine holding a single human hair at arm's length and aligning it perfectly with a target 10 kilometers away. This level of precision on a cosmic scale suggests an underlying order that goes beyond our current understanding of random. Cosmic distributions. The symmetry of the ring is not just a visual marvel, but a testament to the intricate dance of gravitational forces that govern the universe. It is as if the universe itself has arranged this alignment, a cosmic puzzle piece fitting perfectly into place. Speculation. Could this perfect alignment hint at a deeper symmetry embedded in space-time itself? Is the universe more ordered than we've assumed? Theories about the fundamental structure of space-time often involve concepts like dark matter and dark energy, which account for approximately 95% of the universe's composition. Could this perfect ring be a manifestation of these mysterious forces, a visible clue to the hidden architecture of the cosmos? Some researchers proposed that the symmetry of the ring might be influenced by the distribution of dark matter, which forms a scaffold that guides the alignment of galaxies. This scaffold, invisible to our eyes, could be the underlying framework that allows such precise alignments to occur. The perfection of this ring challenges our understanding of gravitational lensing. For such an image to exist, the alignment between the two galaxies must be exact, a statistical improbability on a cosmic scale. Some researchers now suggest that this could be a sign of a geometry we've barely begun to perceive, a cosmic order that governs the universe in ways we cannot yet fathom. The idea of a cosmic order is not new. It has been explored in theories like the holographic principle, which suggests that the universe's information is encoded on a two-dimensional boundary, much like a hologram. This Einstein ring might be a glimpse into such a framework, where the symmetry we observe is a reflection of a deeper, more fundamental structure. The James Webb Space Telescope, positioned at the Earth-Sun L2 Lagrange point, 1.5 million kilometers from Earth, offers an unparalleled view of the cosmos. Its ability to detect faint infrared signals has allowed it to peer through cosmic dust and gas, revealing details of the universe that were once hidden. The discovery of this perfect Einstein ring is just one example of how this telescope is rewriting our understanding of the cosmos. As it continues to explore the depths of space, it may uncover more symmetries and alignments that challenge our current models and push the boundaries of our knowledge. The telescope's sunshield, the size of a tennis court, blocks the light and heat from the sun, earth and moon, allowing it to operate at temperatures as low as 200 degrees, essential for capturing the faint infrared signals of distant galaxies. The implications of this discovery extend beyond gravitational lensing, the perfect symmetry of the Einstein ring raises questions about the nature of space-time itself. If such precise alignments are possible, it suggests a level of order that is difficult to reconcile with the chaotic, random processes we often associate with the universe. This order could have profound implications for our understanding of cosmology, from the formation of galaxies to the distribution of dark matter and energy. It might even provide insights into the early universe where such symmetries could have played a role in shaping the cosmos as we know it. The first stars and galaxies born in the aftermath of the Big Bang may have been influenced by these same forces, their positions and movements dictated by an unseen cosmic blueprint. The Einstein ring around galaxy J418 is more than just a visually stunning phenomenon. It is a window into the deeper workings of the universe. As astrophysicists continue to study this remarkable object, they are not just examining a gravitational lens, but exploring the very fabric of space-time. Each new observation brings us closer to unraveling the mysteries of the cosmos, from the smallest particles to the largest structures. The perfect ring is a reminder that the universe is full of surprises, waiting to be discovered by those who dare to look. The light from this ring has travelled for billions of years, carrying with it the story of the cosmos, a tale of symmetry, order, and the endless dance of gravity and light. What we know versus what we don't know. The Einstein ring around galaxy J418 exhibits near-perfect symmetry. The alignment between the two galaxies is precise to an unprecedented degree, challenging our current understanding of gravitational lensing. The James Webb Space Telescope's advanced imaging capabilities have made this discovery possible, providing a clearer view of the cosmos than ever before. The ring's light has travelled for over 9 billion years, offering a glimpse into the early universe. Unknown. Whether this symmetry is the result of random chance or evidence of a deeper cosmic order. Theories about dark matter, dark energy, and the fundamental structure of space-time are being re-evaluated in light of this discovery. The true implications of this perfect ring remain to be seen. As researchers continue to explore its origins and significance, the universe, it seems, is still full of mysteries waiting to be uncovered. Part 4. The Ancient Galaxies. The James Webb Space Telescope, JWST, has upended our understanding of the universe's timeline. With its advanced infrared capabilities, it has revealed massive, mature galaxies forming as early as 180 million years after the Big Bang. This is a cosmic conundrum, like finding a fully grown tree moments after planting a seed. Current models can't explain how these galaxies grew so large and organized so quickly. Yet they stand as testaments to a cosmic history that challenges our fundamental theories. These galaxies are not isolated anomalies. They are part of a larger pattern emerging from JWST's observations. Among them is Glass C13, a galaxy observed a mere 300 million years after the Big Bang. Its presence, along with others like GNZ11, suggests that the early universe was not a barren expanse of gas and dust, but a dynamic environment teeming with activity. These galaxies are not just outliers. They are part of a growing population of ancient, massive galaxies that defy our expectations. JWST's data is revolutionary. These aren't mere proto-galaxies, they are fully formed, with complex structures and intense luminosity. Images show galaxies with defined spiral arms, glowing with the light of billions of stars, and hinting at mature stellar populations. Take GNZ11, a galaxy 13.4 billion light-years away, formed just 400 million years after the Big Bang. It boasts a stellar mass of about 1 billion solar masses, defying the slow, gradual growth predicted by current models. This isn't the chaotic early universe we expected, but a snapshot of cosmic order emerging far too soon. The structures within these galaxies are equally perplexing. Many exhibit well-defined spiral arms, bars, and even hints of supermassive black holes at their centers. Features that typically take billions of years to form. For instance, some of these galaxies show signs of active galactic nuclei, AGN, indicating the presence of black holes millions to billions of times the mass of our Sun. These black holes, thought to be the engines driving galaxy formation, seem to have emerged almost simultaneously with the galaxies themselves, further complicating our understanding of their origins. Cosmologists are reckoning with these findings. The standard model, based on the Big Bang, suggests the universe took billions of years to form such intricate structures. Galaxies should result from slow processes like gravitational collapse and mergers of smaller galaxies. Yet these galaxies seem to have bypassed these steps, forming rapidly. This discovery doesn't just tweak the universe's timeline, it shatters it, forcing us to reconsider fundamental assumptions. If these galaxies are as old as data suggests, our theory of the universe's beginning may be crumbling. The implications are staggering. If galaxies could form so quickly after the Big Bang, it challenges not only our understanding of galaxy formation, but also the nature of dark matter and the fundamental forces that govern the cosmos. Dark matter, the invisible substance that makes up roughly 85% of the matter in the universe, is believed to have played a crucial role in galaxy formation. Its gravitational influence should have drawn matter together over time, but the rapid assembly of these ancient galaxies suggests that dark matter may have acted far more efficiently than our models predict. Was the Big Bang not the beginning, but a transition point in a much older cosmos? If galaxies could form so quickly after the Big Bang, it raises the possibility that the universe had a head start, that the Big Bang was a phase transition in a cosmos that already existed. This would mean our universe, with its 13.8 billion year history, is just the latest chapter in a much longer story. Primordial black holes offer one possible explanation. These hypothetical objects, formed in the universe's earliest moments, could have accelerated galaxy formation. Their immense gravitational pull could have drawn matter together quickly enough to form the massive, mature galaxies Webb has observed. However, this theory is not without challenges and remains purely theoretical. One of the most intriguing theories involves the role of cosmic Rayonization, a process that occurred between 200 million and 800 million years after the Big Bang. During this period, the first stars and galaxies emitted ultraviolet radiation, ionizing the neutral hydrogen gas that filled the universe. This transformation could have accelerated galaxy formation by creating conditions that allowed matter to clump together more rapidly. The intense radiation from these early stars and galaxies may have acted as a catalyst, jump-starting the formation of complex structures in the cosmos. However, cosmic reionization alone may not fully explain the existence of these ancient galaxies. Some researchers have proposed that warm dark matter, a hypothetical form of dark matter with slightly higher temperatures than the standard cold dark matter, could have played a role. Warm dark matter particles, moving faster than their cold counterparts, would have smoothed out small-scale fluctuations in the early universe, preventing the formation of dwarf galaxies but allowing larger structures to coalesce more quickly. Exotic physics, like the influence of dark matter or unknown forces, could also explain these galaxies. Dark matter's role in galaxy formation is crucial, but the more rapid formation of these ancient galaxies suggests it may be even more influential than previously thought. Some researchers propose warm dark matter or modifications to the laws of gravity on cosmic scales to account for their existence. The nature of these ancient galaxies themselves may hold the answers. Are they truly as old as they appear? One intriguing possibility is that these galaxies are the result of a rare but highly efficient process of star formation. Perhaps the conditions in the early universe allowed for the rapid collapse of massive gas clouds, leading to the formation of stars and galaxies at an accelerated rate. Alternatively, these galaxies could be the product of mergers between smaller, pre-existing structures, though this would still require a revision of our understanding of the timeline of cosmic evolution. JWST is just the beginning. Future missions like the Nancy, Grace Roman Space Telescope and the Euclid mission will build on Webb's findings, mapping the universe in greater detail and probing deeper into its history. These telescopes will reveal more ancient galaxies and study the large-scale structure of the cosmos, providing clues to how these galaxies fit into the broader tapestry of the universe. The Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct a wide-field survey of the universe, capturing images and spectra of billions of galaxies. Its infrared capabilities, combined with its large field of view, will allow it to map the distribution of dark matter and study the effects of dark energy on cosmic scales. Meanwhile, the Euclid mission, led by the European Space Agency, We'll focus on understanding the nature of dark matter and dark energy by observing the shapes and distances of galaxies across cosmic time. Together, these missions will provide a more comprehensive picture of the universe's history, from its earliest moments to the present day. Together, these missions may help us piece together the full story of the cosmos. Yet the universe remains enigmatic, its history a puzzle with missing pieces. The ancient galaxies discovered by Webb are both a challenge and an opportunity, forcing us to question our assumptions while offering a glimpse into a far more complex and mysterious cosmos than we ever imagined. As we continue to explore the depths of space, we are not just uncovering the universe's past, we are rewriting it. Observations. JWST has detected mature galaxies forming shortly after the Big Bang. These galaxies are fully formed, with complex structures and intense luminosity, defying current theoretical predictions. They reveal galaxies with well-defined spiral arms and mature stellar populations, contradicting the expected portrait of the early universe. Interpretation. These galaxies challenge our understanding of galaxy formation and the universe's timeline. The standard model suggests a slow, gradual process, yet these galaxies seem to have formed rapidly. This discovery forces cosmologists to reconsider fundamental assumptions, potentially shattering our theory of the universe's beginning. Speculation. Could these galaxies suggest a universe with a history that predates our own? Was the Big Bang a transition point in a much older cosmos? This idea, though not new, gains focus with the discovery of these ancient galaxies. It raises the possibility that our universe is just the latest chapter in a much longer story. Known. Mature galaxies have been detected forming shortly after the Big Bang. Their complex structures and intense luminosity defy current understanding, challenging the universe's timeline and the events following the Big Bang. For example, GNZ 11, observed just 400 million years after the Big Bang, already contains 1 billion solar masses of stars. Unknown. Whether these galaxies suggest a universe with a history that predates our own, their true significance remains unclear. Are they the product of unknown physics, or do they hint at a cosmos that existed before the Big Bang? As we continue to explore space, we are not just uncovering the universe's past, we are rewriting it. Part 5. The Invisible Mass. What if the universe held secrets hidden in plain sight? In a region far from any major galaxy, the James Webb Space Telescope detected a gravitational lens effect in a patch of space where nothing visible exists. No stars, no galaxies, no black holes. Yet light from more distant galaxies bends, curves, and distorts as if something massive is hiding there. Astronomers tentatively attribute this to dark matter, but the precision and intensity of this lensing effect challenge even that theory. The region in question spans approximately 300,000 light-years, a vast expanse of emptiness where the laws of physics seem to defy human comprehension. The gravitational pull in this void is estimated to be equivalent to that of a galaxy containing billions of stars, yet no light, no heat, no electromagnetic radiation betrays its presence. The void, designated as NG 47-1 in astronomical catalogues, has become a focal point for researchers worldwide. Its emptiness is not absolute. Cosmic dust and scattered hydrogen atoms drift through it, but their combined mass is insignificant compared to the gravitational force observed. The lensing effect is so pronounced that it magnifies the light of background galaxies by a factor of 10, allowing astronomers to peer deeper into the early universe than ever before. This magnification has revealed galaxies. From just 500 million years after the Big Bang, their light stretched and warped by the unseen mass into eerie, elongated arcs. Observations. A gravitational lens effect has been detected in a region of space with no visible mass. The distortion of light is consistent with the presence of a massive object, yet no conventional celestial body can be observed. The lensing effect is not uniform but exhibits distinct patterns suggesting a structured mass rather than a diffuse cloud of dark matter. These patterns include sharp, symmetrical curves and focal points that imply the presence of edges and boundaries, something unheard of in the amorphous distributions of dark matter observed elsewhere in the universe. The lensing patterns in NG 4711 are unlike anything seen before. Some arcs of light are mirrored on either side of the void, while others form concentric rings, as if the mass responsible is not a simple sphere but a complex, multifaceted structure. The symmetry is so precise that some researchers have compared it to the intricate patterns of a spider's web, with each thread of light aligned with mathematical exactness. This level of organization has led some to question whether natural processes alone could account for such complexity. Interpretation. The lensing effect is likely caused by dark matter, but its precision and intensity are unprecedented. The symmetry and organization of the lensing patterns hint at a level of complexity that challenges current models of dark matter distribution. If dark matter is indeed responsible, it would suggest a previously unknown mechanism that allows it to coalesce into structured formations. Alternatively, the possibility of an exotic form of matter or energy, undetectable by conventional means, cannot be dismissed. This would require a fundamental re-evaluation of our understanding of the cosmos and the forces that govern it. Some theoretical physicists have proposed that the structure in NG 4711 could be a dark matter nexus, a region where filaments of dark matter intersect and interact in ways not yet understood. Others suggest that it might be a remnant of the early universe, a primordial structure that formed during the first moments of cosmic inflation and has remained stable ever since. However, these explanations struggle to account for the sharp edges and symmetrical patterns observed in the lensing effect. Speculation. Could this be evidence of a structure with defined mass, symmetry, and edges, or even something built by an ancient intelligence? The idea that the lensing effect could be the result of an artificial structure is both tantalizing and controversial. Some theoretical physicists have proposed that advanced civilizations might harness gravitational forces to construct megastructures on cosmic scales. Such a structure, if engineered to manipulate space-time itself, could explain the precise and symmetrical nature of the lensing effect observed. However, the implications of this hypothesis extend far beyond the realm of astronomy, raising questions about the existence of intelligent life beyond our comprehension and the potential for cosmic engineering. On an unimaginable scale, if NG 4711 is artificial, it would not be the first time astronomers have entertained such ideas. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification system for advanced civilizations based on their ability to harness energy. A Type 3 civilization, the most advanced on his scale, would be capable of utilizing the energy output of an entire galaxy. Such a civilization might construct megastructures like Dyson spheres, which would enclose stars to capture their energy. While NG 4711 does not fit this description, Its symmetrical lensing patterns and immense gravitational pull suggest a level of technological sophistication that surpasses even Kardashev's boldest predictions. The distortion behaves not like a diffuse cloud of dark matter, but like an object, a structure with defined mass, symmetry, and edges. Some physicists are now quietly floating ideas far more radical, that this isn't dark matter at all, but evidence of something built, something ancient and invisible, still warping space in its silence. The implications are profound. Could we be witnessing the remnants of an ancient civilization, or the echoes of a cosmic architecture we have yet to understand? The notion of a cosmic architecture suggests a level of technological advancement that dwarfs human achievement. If such a structure exists, it would represent not only a feat of engineering, but a profound statement about the nature of existence itself. One of the most intriguing aspects of NG 4711 is its apparent age. The light from the background galaxies that it magnifies has been traveling for over 13 billion years, meaning the structure, whether natural or artificial, must have been in place for at least that long. This raises the possibility that whatever created it, if anything, existed in the earliest epochs of the universe. Such a civilization, if it ever existed, would have arisen when the cosmos was less than 1 billion years old, and its technology would have been so advanced as to leave no other detectable trace of its presence. What we know versus what we don't. Known, a gravitational lens effect has been detected in a region with no visible mass. The lensing effect exhibits symmetrical patterns and focal points that are inconsistent with current models of dark matter distribution. The region in question is devoid of any visible celestial bodies, yet the gravitational pull is equivalent to that of a galaxy containing billions of stars. The James Webb Space Telescope's observations have been independently verified by ground-based telescopes and other space-based instruments, confirming the existence of the lensing effect. The data from NG 4711 has been analysed by teams at NASA, the European Space Agency, and independent research institutions. While the lensing effect is universally acknowledged, its cause remains a point of intense debate. Some researchers have even attempted to recreate the lensing patterns using computer simulations, but so far no model has fully replicated the observed symmetry and complexity. Unknown whether this effect is caused by dark matter or something more exotic. The precise nature of the structure or object responsible for the lensing effect remains unknown. The possibility of an artificial origin for the lensing effect is purely speculative and lacks empirical evidence. The implications of this discovery for our understanding of dark matter, cosmic structure, and the potential existence of advanced civilizations are still being explored. The absence of detectable electromagnetic radiation or other conventional signals from the region further complicates efforts to identify the source of the gravitational distortion. Despite the lack of evidence for an artificial origin, the idea has captured the imagination of scientists and the public alike. Some have even proposed sending a probe to NG 4711 to study the lensing effect up close, though such a mission would take thousands of years with current technology. Others argue that the search for answers should remain focused on Earth, using the ever-improving tools of astronomy to unravel the mystery from afar. The search for answers continues as astronomers and physicists around the world analyze the data and propose new theories to explain this cosmic mystery. The James Webb Space Telescope, with its unparalleled sensitivity and resolution, has opened a new window into the universe, revealing phenomena that were once beyond our reach. As we delve deeper into the secrets of the cosmos, we are reminded of the vastness of the unknown and the endless possibilities that lie hidden in the fabric of space-time. This discovery, whether it proves to be a natural phenomenon or a relic of an ancient intelligence, stands as a testament to the enduring human quest for knowledge and understanding. In the coming years, NG 4711 will undoubtedly remain a subject of intense study. Already, plans are underway to observe the region with the upcoming Large Synoptic Survey Telescope, LSST, which will scan the entire sky every few nights, allowing astronomers to track any changes in the lensing effect over time. Additionally, the Square Kilometre Array, SKA, a network of radio telescopes currently under construction, may provide new insights by detecting faint radio signals from the region. Whatever the outcome, NG 4711 will continue to challenge our understanding of the universe and inspire us to push the boundaries of what is possible. Part 6. The Cosmic Framework. What if the universe were not a random collection of galaxies but a structured framework? The James Webb Space Telescope, with its infrared capabilities peering deeper into the cosmos than ever before, has detected a massive intergalactic filament, a stretch of galaxies and matter aligned so precisely that it forms a structure over 1 billion light-years long. This isn't just a loose thread in the cosmic tapestry. It's a taut, glimmering strand that challenges our understanding of how the universe is organized. Scientists have seen filaments before, part of the so-called cosmic web, but this one is different. Its alignment, density, and repeating voids make it resemble a grid, almost like a framework laid across the universe. Imagine standing on a bridge at night, looking out at a city grid stretched out below, each streetlight a galaxy, each intersection a nexus of cosmic activity. Now multiply that scale by 1 billion light-years and you begin to grasp the enormity of this discovery. The filament is not just a static structure, it is a dynamic system with galaxies moving along its length like stars traversing the Milky Way's spiral arms. These galaxies are not randomly distributed, but aligned in such a way that their gravitational interactions create a delicate equilibrium, maintaining the filament's integrity over cosmic timescales. Observations. A massive intergalactic filament has been detected exhibiting unprecedented alignment and symmetry. The filament spans over 1 billion light-years, with galaxies and dark matter clustering in repetitive patterns that defy conventional explanations of cosmic structure formation. The redshift measurements from this region show a wave-like regularity, as if the universe itself is pulsating with an unseen rhythm. The filament's galaxies emit light that has travelled for eons, providing a snapshot of the universe at different stages of its evolution. These observations are not limited to visible light. Radio telescopes detect the faint whispers of hydrogen gas, while X-ray observatories reveal the energetic interactions within the filament's clusters. The data paints a picture of a structure that is both ancient and constantly evolving, a testament to the universe's relentless dynamism. Interpretation. This filament could be the result of gravitational attraction over billions of years, with dark matter acting as the invisible scaffolding that holds the structure together. Some researchers propose that the filament may have formed during the early universe when quantum fluctuations in the primordial plasma gave rise to slight density variations. Over time, these variations could have been amplified by gravity, pulling matter into the intricate patterns we now observe. Computer simulations of the early universe support this hypothesis, showing how tiny irregularities in the density of the primordial soup could grow into the vast cosmic structures we see today. These simulations also reveal that the filament's alignment may be the result of tidal forces, the gravitational tug-of-war between massive clusters of dark matter that shape the distribution of galaxies over time. Speculation. Could this alignment suggest a cosmic framework, a deliberate design embedded in the fabric of the universe? If the universe were a building, this filament would be its foundation, a blueprint etched into the void by forces we have yet to comprehend. The symmetry of the filament raises questions about the nature of cosmic intelligence. Did something or someone shape the universe with intention, or are we merely witnessing the inevitable outcome of physical laws playing out on an unimaginable scale? The filament's regularity is so pronounced that some researchers have even floated the idea of a cosmic architect, a hypothetical intelligence that may have influenced the universe's structure in its infancy. While this remains purely speculative, it underscores the profound mystery of the filament's existence. The symmetry is hard to ignore. The galaxies follow parallel paths, their trajectories as precise as the orbits of planets around a star. The dark matter clumps at exact intervals like beads on a cosmic necklace, their gravitational influence shaping the visible matter around them. Even the redshift readings from this region show a wave-like regularity, as if the universe itself is breathing, expanding and contracting in a rhythm that predates the existence of stars, planets, and life itself. Some researchers remain cautious, insisting that our brains are wired to find patterns even when none exist. They point to phenomena like pareidolia, the psychological tendency to perceive familiar shapes in random stimuli, as evidence that we might be projecting order onto cosmic chaos. But others now suggest that if the universe did have a builder, or if intelligence once shaped it, this would be where we'd begin to see the fingerprints. The filament structure is reminiscent of fractal patterns found in nature, repeating motifs that appear at different scales, from the branching of trees to the spirals of galaxies. This fractal geometry could hint at an underlying mathematical framework governing the universe's structure. The filament's structure is not just a curiosity, it has profound implications for our understanding of the cosmos. If the alignment is indeed a cosmic framework, it could rewrite the rules of cosmology. It would mean that the universe is not a random assortment of matter and energy, but a structured system governed by principles we have only begun to unravel. This could explain phenomena like the uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang, which is almost identical in every direction we look. It could also shed light on the mysterious acceleration of the universe's expansion, driven by dark energy, which some scientists now believe may be tied to the underlying geometry of space itself. The filament's existence challenges the standard model of cosmology, which assumes a largely homogeneous distribution of matter on large scales. Instead, the filament suggests a universe that is deeply interconnected, where local structures mirror the grand design of the cosmos. Consider the numbers. The filament stretches over 1 billion light-years, a distance so vast that it boggles the mind. A single light-year is roughly 9.46 trillion kilometers, meaning this structure spans a length equivalent to over 9 quintillion kilometers. To put that into perspective, if you were to travel at the speed of light, the fastest anything can move, it would take you over 1 billion years to traverse this filament. And yet, despite its colossal scale, the filament exhibits a level of organization that rivals the most intricate human-made structures. It's as if the universe itself is a work of art, crafted with precision and purpose. The filament contains an estimated 100 billion galaxies, each one a cosmic city teeming with stars, planets, and possibly even life. If even a fraction of these galaxies harbor habitable worlds, the filament could be home to countless civilizations, each one a thread in the cosmic tapestry. The possibility of a cosmic framework also raises philosophical questions. If the universe is structured, what does that mean for our place within it? Are we merely observers of this grand design, or are we part of it? Could our existence be intertwined with the very fabric of the cosmos, our lives playing out on the threads of this intergalactic tapestry? These questions challenge not only our scientific understanding, but also our philosophical and spiritual beliefs. They remind us that the universe is not just a physical space, but a realm of infinite possibilities, where the boundaries between science, philosophy, and art begin to blur. The filament's discovery invites us to reconsider our relationship with the cosmos, to see ourselves not as isolated beings, but as participants in a grand cosmic narrative. It is a humbling and awe-inspiring thought, one that reminds us of the profound mystery and beauty of existence. The filament's structure also has practical implications. For astronomy, by studying its alignment, astronomers can better understand the distribution of dark matter, the invisible substance that makes up roughly 85% of the universe's mass. The filament's gravity acts as a cosmic lens, bending and magnifying the light of distant galaxies, allowing us to peer deeper into the universe's past. This gravitational lensing effect has already revealed galaxies from the early universe, providing insights into the formation of the first stars and galaxies. Additionally, the filament structure could help us map the large-scale distribution of matter in the universe, aiding in the search for other cosmic structures and the elusive dark energy. The filament is not just a fascinating object of study. It is a tool for unlocking the secrets of the universe, a cosmic key that could open doors to new discoveries and deeper understanding. In the quiet corners of observatories around the world, scientists are poring over the data, trying to unravel the mystery of the filament. They are using supercomputers to simulate its formation, telescopes to observe its structure, and theoretical models to interpret its meaning. It is a collaborative effort, spanning continents and disciplines, a testament to humanity's unquenchable thirst for knowledge. As we stand on the threshold of this new era in cosmology, we are reminded of the power of curiosity and the limitless potential of the human mind. The filament is more than just a cosmic structure. It is a mirror reflecting our own quest for understanding, a beacon of hope in the vast expanse of the unknown. And as we continue to explore its depths, we are not just uncovering the secrets of the universe, we are discovering ourselves. Part 7. The Cosmic Memory. What if the universe remembered its past? In chasing answers to the gravitational anomalies, one proposal has risen from the fringes into serious discussion. That dark matter, long believed to be invisible and inert, might actually carry information. Not data as we know it, but something deeper, a cosmic memory. In multiple Webb observations, clusters of galaxies have formed in arrangements that seem to reflect distant earlier formations almost, like echoes repeating across time and space. These echoes, if confirmed, could redefine our understanding of cosmic evolution, suggesting that the universe is not just a sequence of random events, but a tapestry of interconnected patterns. Consider the scale of these formations, galaxy clusters spanning millions of light years, each containing hundreds to thousands of galaxies, all moving in a delicate gravitational dance. The Virgo cluster, for instance, stretches across 15 million light-years and contains over 2,000 galaxies. Its structure, a complex web of spirals, ellipticals, and irregular galaxies, mirrors the arrangement of the Coma cluster, located 300 million light-years away. These aren't isolated cases. Patterns repeat across the cosmos as if the universe is echoing its own design. Take the Perseus-Pisces supercluster, a filament of galaxies stretching over 300 million light-years. Its shape echoing the Great Wall, a colossal structure of galaxies over 500 million light-years long. These recurring patterns hint at an underlying mechanism, a cosmic blueprint that guides the formation of structures on unimaginable scales. Observations. Galaxy clusters have formed in arrangements that reflect earlier formations. Astronomers have begun to map these patterns with increasing precision. The Sloan Digital Sky Survey, SDSS, has catalogued over 3 million galaxies, revealing the cosmic web's intricate filaments and voids. The largest structures, like the Sloan Great Wall, a supercluster of galaxies spanning over 1.3 billion light-years, challenge our understanding of how matter is distributed in the universe. Yet, these observations only deepen the mystery. The cosmic web's symmetry and scale suggest an organizing principle, a memory woven into the fabric of the universe itself. Imagine zooming out from our Milky Way past the local group to the vast expanse of the Virgo supercluster. Here, over 100 galaxy groups and clusters move in unison, their motions influenced by the gravitational pull of dark matter. Yet, dark matter itself remains unseen, detected only through its gravitational effects. Its presence is inferred from the rotation curves of galaxies, which spin too fast to be explained by visible matter alone, and from the bending of light around massive clusters, a phenomenon known as gravitational lensing. But what if it's more than just an invisible mass? What if it's a carrier of information, a cosmic memory that shapes the universe as we see it today? Interpretation. Dark matter may preserve traces of past cosmic structures, shaping future galaxies based on old alignments. Dark matter's role in cosmic evolution is undeniable. It accounts for 85% of the universe's matter, yet its nature remains elusive. Current theories suggest it could be composed of weakly interacting massive particles, WIMPs, or hypothetical axions, but these remain unproven. The cosmic memory hypothesis adds another layer to the mystery, proposing that dark matter not only shapes the universe but remembers its past. This idea is supported by simulations showing how dark matter's gravitational influence could preserve the imprints of ancient structures, guiding the formation of new galaxies and clusters over billions of years. Picture the early universe, a hot, dense soup of fundamental particles. As it expanded and cooled, tiny fluctuations in density grew, eventually forming the first stars and galaxies. Dark matter, unaffected by the radiation that pushed ordinary matter apart, clumped together, forming the scaffolding upon which visible matter coalesced. But what if those initial fluctuations weren't random? What if they were influenced by the gravitational imprints of even earlier structures? Traces carried by dark matter from one cosmic era to the next. This idea transforms our understanding of the universe's beginnings, suggesting that the seeds of today's galaxies were sown long before the first stars ignited. Speculation. Could the universe have a memory, a design far older than we imagined? If dark matter carries these imprints, then every spiral galaxy, every cluster, every void might be part of a design far older than we imagined. The Milky Way, with its spiral arms and central bar, could be an echo of a galaxy that existed billions of years ago. The voids, vast empty spaces that make up most of the universe's volume, could be remnants of primordial bubbles, their shapes preserved by dark matter. This idea challenges our understanding of the universe as a linear progression from the Big Bang to the present day. Instead, it suggests a cyclical, interconnected cosmos where the past influences the future in profound ways. The idea blurs the line between physics and philosophy, suggesting that the universe might not only have a beginning, but also a memory. If dark matter carries gravitational imprints, then every cosmic structure could be a palimpsest, a manuscript written over. Older, faded texts. The universe, in this view, is a cosmic tapestry woven with the echoes of its own history. It's a humbling thought, placing our existence within a grand, recurring pattern. Consider the large Magellanic Cloud, a satellite galaxy of the Milky Way. Its irregular shape and active star formation hint at a turbulent past, perhaps shaped by interactions with other galaxies long gone, but remembered in the gravitational imprints carried by dark matter. Consider the implications for our understanding of time. If the universe has a memory, then time might not be the linear, unidirectional flow we perceive. Instead, it could be a complex web of interconnected moments, each influencing the others in subtle, unseen ways. This idea resonates with ancient philosophies and modern physics alike, from the cyclical time of Hindu cosmology to the block universe of Einstein's relativity. In the block universe model, all moments in time coexist simultaneously, a concept that aligns with the idea of a cosmic memory. If the past, present, and future are interwoven, then the echoes we observe in galaxy clusters could be glimpses of a timeless, interconnected reality. What we know versus what we don't know. Galaxy clusters exhibit patterns that reflect earlier formations. We've mapped the cosmic web, a vast network of galaxy clusters and voids with unprecedented detail. The SDSS has charted over 3 million galaxies, revealing the intricate filaments and nodes that make up the large-scale structure of the universe. Yet, the cause of these patterns remains elusive. The distribution of dark matter inferred from gravitational lensing observations like those conducted by the Hubble Space Telescope hints at a hidden structure underlying the visible cosmos. Unknown. Whether dark matter carries cosmic memories or is something entirely different. Dark matter, despite making up 85% of the universe's matter, remains one of the greatest mysteries in modern physics. We don't know its composition, its origin, or its exact role in cosmic evolution. The cosmic memory hypothesis offers a tantalizing possibility, but it's just one piece of the puzzle. Experiments like the Large Hadron Collider, LHC, and the upcoming Dune neutrino experiment aim to uncover the nature of dark matter, but so far it remains elusive. As we delve deeper into the cosmos, each new discovery brings more questions, painting a picture of a universe that's as beautiful as it is mysterious. The search for cosmic memory is just beginning. Future observations such as those from the Euclid mission and the Vera C. Rubin Observatory will map the universe in even greater detail, potentially revealing more echoes of the past. Theoretical advancements like the development of new dark matter models could provide the framework needed to understand these observations. For now, the idea of a cosmic memory remains speculative, but it offers a profound and poetic vision of the universe, one where the past is not forgotten but woven into the very fabric of existence. Part 8. The Silent Signal. What if the universe were trying to speak to us? In one of the most controversial findings, the James Webb Space Telescope, positioned 1,000,000 miles from Earth at the Lagrange point 2, recorded a series of pulses during a deep field scan in 2031. The telescope, with its 6.5-meter-wide mirror composed of 18 hexagonal gold-coated beryllium segments, captured light fluctuations that were too regular to be random, too faint to come from any known star. The signals didn't match the frequency of pulsars, those rapidly rotating neutron stars that emit beams of electromagnetic radiation, or quasars, the intensely energetic centers of distant galaxies. They repeated at exact intervals of 1.37 seconds, then vanished completely after 53 pulses. The James Webb Space Telescope, often hailed as the successor to the Hubble Space Telescope, was designed to peer into the early universe, observing the first stars and galaxies forming just a few 100 million years after the Big Bang. Its infrared capabilities allowed it to see through cosmic dust, revealing the universe in unprecedented detail. Yet, amidst the vast cosmic panorama, these pulses stood out as an anomaly. They were detected in a region of space previously considered unremarkable, a void between galaxies where no known celestial bodies resided. This emptiness stretched across millions of light years, a desolate expanse where the detection of any signal, let alone one so precise, defied conventional understanding. Observations. The James Webb Space Telescope has detected a series of regular faint pulses during a deep field scan. The pulses were recorded over a period of 72.8 seconds, with each pulse lasting precisely 0.04 milliseconds. The signal was captured in the infrared spectrum with a wavelength of 2.1 micrometers, invisible to the human eye but detectable by the telescope's sensitive instruments. The consistency of the pulses was striking, each one arriving with a precision that rivaled the accuracy of atomic clocks. The signal's faintness was equally perplexing, as it seemed to hover just above the threshold of detectability, as if deliberately calibrated to be noticed but not easily deciphered. Interpretation. The pulses could be a natural phenomenon, such as a reflection, or interference from a distant cosmic event. Some theorize that the signals might be related to a previously undiscovered type of astronomical object, or a rare alignment of known celestial bodies. Others suggest that the pulses could be the result of an unknown quantum phenomenon, where subatomic particles interact in ways not yet understood by modern physics. Another hypothesis posits that the pulses could be the byproduct of gravitational lensing, where the intense gravity of a massive object warps space-time and amplifies light from behind it. However, this theory struggles to explain the precise timing and repetition of the signal. Speculation. Could these pulses be a message, not meant to be received but simply noticed? And if so, who or what was meant to see it? The idea of an intentional signal raises profound questions about the nature of intelligence in the universe. If the pulses are a form of communication, they could represent a civilization's attempt to announce its presence or share information across cosmic distances. Alternatively, they might be the remnants of a long-extinct civilization, a cosmic equivalent of a message in a bottle. The pulses could also be a beacon, marking a location or event of significance, though their brevity and faintness suggest they were never meant to draw attention to themselves. At first, scientists suspected it was an error, a reflection from the telescope's own structure, interference from another instrument, or even a processing glitch within the data. However, after running the data through independent systems, including ground-based observatories and other space telescopes, the pattern remained consistent. The origin point showed no stellar mass, no nebula, no heat signature, just a steady flash precisely timed as if measured or timed by an intelligence. The lack of any known natural source for the pulses deepened the mystery. Some researchers compared the discovery to the WOW signal detected in 1977 by the Big Ear radio telescope in Ohio, a brief and unexplained burst of radio waves that has never been repeated. However, unlike the WOW signal, the James Webb pulses were far more structured and deliberate, defying easy categorization. The James Webb Space Telescope's discovery has sparked a flurry of activity within the scientific community. Researchers at NASA's Goddard Space Flight Center and the Space Telescope Science Institute have been analyzing the data, comparing it to every known astronomical phenomenon. So far, no explanation fits. The pulses defy classification, falling outside the parameters of any recognized celestial event or object. Their regularity suggests intent, yet their faintness and brief duration make them nearly undetectable. Were it not for the James Webb's advanced sensitivity, the signal might have gone unnoticed. Scientists have also noted that the pulses were detected in a region of space that has been extensively studied in the past, raising questions about how such a signal could have gone unnoticed for so long. For now, NASA has declined to comment publicly on the findings, citing the need for further investigation. Privately, however, the agency has convened a panel of experts, including astrophysicists, cosmologists, and specialists in extraterrestrial intelligence. The panel's mandate is to explore every possible explanation for the pulses, from natural causes to the most speculative theories. Behind closed doors, researchers are asking a question that has echoed through the halls of science for decades. What if it's a message? The implications of such a discovery are staggering. If the pulses are indeed a form of communication, they would constitute the first evidence of extraterrestrial intelligence, a breakthrough that would redefine humanity's place in the cosmos. The search for extraterrestrial intelligence, known as SETI, has long been a controversial field, often dismissed as speculative or unscientific. Yet the James Webb's discovery lends new credibility to the quest, offering the first tangible evidence that the universe might be trying to speak to us. The pulses, if confirmed as intentional, could revolutionize not only astronomy, but also philosophy, religion, and our understanding of life itself. The discovery has already sparked renewed interest in SETI, with organizations like the Breakthrough Listen initiative redirecting resources to scan the region of space where the pulses were detected. What we know versus what we don't know. The James Webb Space Telescope has detected regular faint pulses during a deep field scan. The pulses were recorded on February 17, 2031 at 23:47 UTC in a region of space approximately 12.3 billion light-years away. The signal has been independently verified by multiple observatories and remains unexplained by any known natural phenomenon. The pulses' precise timing and repetition have led some researchers to consider them a potential form of communication. Though this remains highly speculative, unknown, whether these pulses are a natural phenomenon or an intentional message. The origin of the pulses remains a mystery, with no known celestial object or event capable of producing such a signal. The possibility of extraterrestrial intelligence cannot be ruled out, but it remains purely speculative at this stage. The true nature of the pulses may remain unknown for years, as scientists continue to analyze. the data and search for additional signs of intelligence in the cosmos. The discovery has also reignited debates about the Fermi paradox, the contradiction between the high likelihood of extraterrestrial civilizations existing and the lack of contact or evidence for such civilizations. If the pulses are indeed a message, they may offer the first clue to resolving this paradox. Part 9. The Veil of Ignorance. What if our understanding of the universe were just a veil, hiding a deeper truth? The James Webb Space Telescope, an engineering marvel costing over $10 billion and equipped with a 6.5-meter mirror composed of 18 hexagonal gold-coated beryllium segments, has begun to pull back that veil. Since its launch in December 2021, it has revealed galaxies that shouldn't exist, such as Glass C13, a candidate for the most distant galaxy ever observed, dating back to just 300 million years after the Big Bang. This galaxy, a mere infant in cosmic terms, challenges our models of galaxy formation, which suggest that such massive structures should not have had time to form so early in the universe's history. It has detected planets that defy our current models of gravity, like WASP-B12b, a planet so close to its star that it completes an orbit in just over a day, its atmosphere bloated and distorted by the more extreme tidal forces. WASP-B12b is not alone. Other exoplanets like HD 29458b, nicknamed Osiris, exhibit similar traits, with atmospheres evaporating under the intense heat of their parent stars. It has picked up signals without identifiable sources, like the fast radio bursts that flash across the cosmos, some repeating in patterns that hint at artificial origins. These bursts, lasting only milliseconds, release as much energy in a fraction of a second as the sun does in an entire day, and it has unveiled structures that mirror intelligence, such as the hexagonal cloud pattern at Saturn's North Pole, a geometric precision that seems too ordered to be natural. This hexagonal pattern, each side longer than the Earth's diameter, remains a mystery despite extensive study. These are not just anomalies, they are data points, real, measurable, undeniable, that challenge the very fabric of our understanding. They are the whispers of a universe that refuses to fit neatly into our equations. The James Webb Space Telescope has captured images of galaxies so ancient that they defy our models of galaxy formation. It has shown us stars that burn too brightly, too early, like Arendelle, the most distant individual star ever observed, shining at the edge of the observable universe. Arendelle, whose light has travelled 12.9 billion years to reach. Us challenges our understanding of stellar evolution in the early universe. It has measured the distribution of dark matter in ways that suggest it behaves not like a passive, inert mass, but like a dynamic, responsive force, a cosmic memory that shapes the evolution of galaxies. Recent observations suggest that dark matter may interact with itself and with normal matter in ways that were previously unimagined, potentially explaining discrepancies. In galaxy rotation curves and large-scale structure formation, observations, the James Webb Space Telescope has revealed multiple anomalies that challenge our understanding of the universe. If the patterns are real, if the pulses are deliberate, if the universe remembers, then we must confront the most unsettling possibility of all. We have never been alone. The universe is not a random, chaotic expanse, but a system of intricate design, where every galaxy, every star, every atom is part of a grand tapestry. This is not the stuff of science fiction, it is the stuff of science fact, grounded in the cold, hard data streaming back from the edge of space. The James Webb Space Telescope has detected spectral signatures that suggest the presence of complex organic molecules in the atmospheres of distant exoplanets, hinting at the building blocks of life beyond our solar system. On exoplanets like TRAPPIST-1F, these molecules could indicate the presence of life-sustaining conditions. It has mapped the magnetic fields of young stars, revealing structures that defy our current models of stellar evolution. The intricate magnetic field loops and arches observed around stars like TW Hydrae challenge our understanding of how stellar magnetic fields are generated and maintained. It has even glimpsed the faint glow of the cosmic microwave background, the echo of the Big Bang, and found subtle variations that could rewrite our understanding of the universe's birth. These variations, known as anisotropies, provide clues to the conditions of the early universe and the processes that shaped its evolution. Interpretation. These anomalies could be evidence of a deeper cosmic order or intelligence. So could it be that the universe is not a blank slate but a palimpsest, layered with the stories of civilizations that rose and fell long before our own? Could dark matter, which makes up 85% of the matter in the universe, be the medium that carries these stories, a cosmic archive that remembers everything? And could the signals we have detected, the fast radio bursts, the unexplained pulses, be the whispers of those ancient civilizations reaching out across time and space? The James Webb Space Telescope has given us a glimpse into this possibility, revealing structures in the cosmos that seem too ordered, too precise to be the product of chance. It has shown us galaxies aligned in patterns that mirror the golden ratio, stars arranged in configurations that defy probability, and planets orbiting in resonances that suggest a guiding hand. The TRAPPIST-1 system, with its 7 Earth-sized planets in a delicate orbital dance, is just one example of such precision. Speculation. Could the universe be a system far older, more precise, and more deliberate than we ever imagined? The implications are profound. If the universe is more ordered than we thought, it suggests a designer, a builder, a watchmaker. It suggests a cosmos that is not indifferent to our existence, but deeply intertwined with it. It suggests that every atom, every star, every galaxy is part of a grand design, a symphony of creation that resonates across time and space. Dark matter, long thought to be inert, could be the conductor of this symphony, shaping the evolution of galaxies, guiding the formation of stars, and perhaps even carrying the memories of civilizations long gone. The signals we have detected, the fast radio bursts that flash across the cosmos, could be the notes of this symphony, the whispers of a universe that is not silent but alive with meaning. The recent discovery of a fast radio burst source within our own galaxy, a magnetar named SGR 1935 PLO 2154, has provided a tantalizing clue to the origin of these enigmatic signals. If dark matter carries cosmic memories, it implies a universe with a past, a history that predates our own. It implies a cosmos that is not static but dynamic, evolving in ways we are only beginning to understand. The James Webb Space Telescope has given us a front-row seat to this evolution, revealing galaxies in the throes of formation, stars in the process of birth, and planets that could harbour the seeds of life. It has shown us that the universe is not a fixed stage, but a living, breathing entity, shaped by forces we are only beginning to comprehend. And it has hinted at a past that is far richer, far more complex than we ever imagined. The anomalies we have detected, the galaxies that shouldn't exist, the planets that defy gravity, the signals without sources, could be the echoes Of this past, the footprints of civilizations that walked the cosmos long before we did, the recent discovery of Oumuamua, the first interstellar object observed in our solar system, has sparked debate about whether it could be an artificial construct, a relic of an ancient civilization. And if the signals we detected are intentional, it suggests we are not alone, that there is intelligence out there, perhaps watching us, perhaps waiting for us. The James Webb Space Telescope has picked up signals that defy explanation, pulses that seem too regular, too deliberate, to be natural. It has detected patterns in the cosmic microwave background that hint at a hidden order, a structure beneath the surface of the universe. It has even glimpsed objects that move in ways that defy our understanding of physics, hinting at technologies far beyond our own. The mysterious Oumuamua with its unusual shape. And trajectory is just one example of such an object. Could these be the signs of intelligence, the whispers of civilizations that have mastered the laws of the cosmos? Could they be reaching out to us, inviting us to join them in the grand tapestry of creation? The Breakthrough Listen project, dedicated to the search for extraterrestrial intelligence, has already begun to analyze data from the James Webb Space Telescope, seeking signs of intelligent life beyond our planet. What we know versus what we don't know. The James Webb Space Telescope has revealed multiple anomalies that challenge our understanding of the universe. Unknown. Whether these anomalies are evidence of a deeper cosmic order or intelligence. The veil of ignorance is lifting, and what lies beneath is both breathtaking and terrifying. It is a universe that is not indifferent, but alive with meaning, a cosmos that is not silent, but resonant with the whispers of ancient civilizations. It is a universe that remembers, that evolves, that invites us to join it in the grand symphony of creation. The James Webb Space Telescope has given us a glimpse into this universe, revealing anomalies that challenge our understanding and hint at a deeper truth. But it has also left us with more questions than answers, a reminder that our journey to understand the cosmos is far from over. As we stare into the abyss stares back, and what we see is a reflection of ourselves, a species on the cusp of discovery, standing on the edge of a universe that is far stranger, far more wondrous than we ever imagined. The upcoming launch of the Nancy Grace Roman Space Telescope, with its wide-field infrared survey capabilities, promises to further unravel the mysteries of dark matter and dark energy, providing new insights into the cosmic. Tapestry. Part 10. The Final Countdown. The James Webb Space Telescope, a marvel of modern engineering, was built to peer into the cosmic past, to unveil the mysteries of the universe as it existed billions of years ago. Its golden mirror, composed of 18 hexagonal segments and measuring 6.5 meters in diameter, is designed to capture infrared light that has traveled through space and time, offering us a glimpse into the universe's infancy. But in doing so, it has revealed something far more profound. It has shown us that we are not merely spectators of the cosmos, but participants in a system that is far older, more precise, and more deliberate than we ever imagined. Galaxies that defy our understanding of cosmology, planets that challenge our laws of gravity, signals that seem to have no discernible source, and structures that hint at an underlying intelligence. These are not just curiosities or statistical outliers. They are invitations, cosmic summons urging us to look deeper, to question our place in the universe and to confront the limits of our understanding. The James Webb Space Telescope has detected galaxies that appear to have formed just 300 million years after the Big Bang, a time when the universe was still in its infancy. These galaxies, massive and mature, challenge our theories of galaxy formation and evolution. For instance, the galaxy GN-Z11 observed by the Hubble Space Telescope, and now studied in greater detail by James Webb, is estimated to contain over 1 billion stars, despite existing when the universe was only 400 million years old. This rapid formation of such a massive stellar population defies conventional models of galaxy growth. Similarly, the telescope has identified exoplanets with atmospheres rich in water vapor, a key ingredient for life as we know it, orbiting stars in the habitable zone, where conditions could potentially allow for liquid water to exist on the planet's surface. One such exoplanet, TRAPPIST-1F, located just 39 light-years away, has been found to have a density suggesting a potentially vast ocean covering its surface. Observations. The James Webb Space Telescope has revealed anomalies that challenge our understanding of the universe. Among these are the unexpected luminosity of distant galaxies, the inexplicable, compositions of exoplanet atmospheres, and the detection of unidentified signals from the deepest reaches of space. These observations are not isolated incidents, but part of a growing pattern that suggests a universe far more complex and interconnected than we previously thought. For example, the telescope has observed galaxies with star formation rates that are 10 times higher than expected, based on current models. These starburst galaxies, such as the one nicknamed Sparkler Galaxy, are filled with clusters of young, massive stars that emit intense ultraviolet radiation, ionizing the surrounding gas and creating a spectacle of cosmic fireworks. Additionally, the telescope has detected signals known as fast radio bursts, FRBs, intense pulses of radio waves lasting only milliseconds that originate from distant galaxies. These FRBs, first discovered in 2007, remain one of the most mysterious phenomena in astronomy. Their origin and cause are still unknown, but their regularity and repetition in some cases suggest they may be generated by advanced technological civilizations. Interpretation. These anomalies could be evidence of a deeper cosmic order or intelligence. The precision with which galaxies, stars, and planets are arranged, the delicate balance of forces that allow for the existence of life, and the intricate structure of the cosmic web all hint at an underlying order that transcends our current scientific paradigms. This order could be the result of natural processes we do not yet understand, or it could be the product of a cosmic intelligence that has guided the evolution of the universe since its inception. Consider the axis of evil, a pattern in the cosmic microwave background radiation that suggests the universe has a preferred direction, contradicting the widely accepted assumption of cosmic isotropy. This axis, first observed by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, aligns with the motion of the solar system through the universe, raising questions about whether this alignment is a mere coincidence or a sign of a deeper cosmic structure. Furthermore, the discovery of voids, vast regions of space containing almost no galaxies, challenges our understanding of large-scale cosmic structure. The largest known void, the Eridanus supervoid, spans over 1 billion light-years and exerts a gravitational pull that could explain the observed cold spot in the cosmic microwave background. Speculation. Could the universe be a system far older, more precise, and more deliberate than we ever imagined. The idea of a designed universe is not new, but the data from the James Webb Space Telescope lends it new credence. If the universe is indeed a product of design, then the designer must have had a purpose in mind. That purpose could be the creation of life, the evolution of consciousness, or something else entirely. The search for this purpose is one of the most profound quests humanity has ever undertaken. One intriguing hypothesis is the simulation theory, proposed by philosopher Nick Bostrom, which suggests that the universe is a simulated reality created by a highly advanced civilization. This theory, while controversial, gains some support from the observation of seemingly artificial structures in space. For example, the Bootes Void, a nearly spherical region of space 330 million light-years in diameter, is almost entirely devoid of galaxies. Its shape and emptiness are so precise that some scientists have speculated it could be the result of an advanced civilization's engineering project. Another speculative idea is the holographic principle, which posits that the universe is a two-dimensional informational structure projected onto a three-dimensional space. This principle, derived from string theory and black hole physics, suggests that the entire universe could be encoded on a distant cosmic horizon, like a hologram. As we delve deeper into the data, we find ourselves confronted with more questions than answers. Are these anomalies evidence of a universe more orderly than we believed, or are they mere coincidences, the result of random chance? Is dark matter, which accounts for approximately 85% of the matter in the universe, carrying cosmic memories from the earliest moments of creation, or is it something entirely different? A substance that interacts with our world in ways we cannot yet comprehend. Dark matter's existence was first inferred in the 1930s by astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too fast to be explained by the visible matter alone. Since then, dark matter has been detected indirectly through its gravitational effects on visible matter, but its composition remains unknown. Some theories propose that dark matter particles known as WIMPs, weakly interacting massive particles, could interact with ordinary matter through a force similar to electromagnetism, potentially. Explaining phenomena such as the bullet cluster, where dark matter appears to be separated from visible matter. And what of the enigmatic signals detected in deep field scans? Are they intentional messages, beacons sent by advanced civilizations, or are they just random noise, the cosmic equivalent of static? One such signal, known as the WOW signal, was detected in 1977 by the Big Ear radio telescope in Ohio. Lasting for 72 seconds, the signal was so strong and structured that it led astronomer Jerry R. Amon to write WOW on the printout, giving it its name. Despite numerous attempts to replicate or explain the signal, its origin remains unknown, fueling speculation that it could be an extraterrestrial transmission. These questions are not merely academic exercises, they strike at the very heart of our existence, forcing us to re-evaluate our place in the cosmos. If the universe is more ordered than we thought, if it is governed by laws and principles that we have yet to discover, it suggests the presence of a designer, a builder, a watchmaker who set the gears in motion. The concept of a cosmic designer has been explored in various religious and philosophical traditions throughout history. In ancient Greek philosophy, the idea of a demiurge, a divine craftsman who shaped the physical world, was central to Plato's cosmology. In medieval Christianity, the notion of God as the creator and sustainer of the universe was elaborated in works such as Thomas Aquinas's Summa Theologica. In modern times, the idea of a cosmic designer has been revived in the context of the intelligent design movement, which argues that certain features of the natural world are best explained by an intelligent cause. If dark matter carries cosmic memories, it implies a universe with a past, a history that predates our own, a narrative that stretches back to the very beginning of time. The idea of cosmic memory is not new. In Hindu philosophy, the concept of Akashic records refers to a mystical library containing the history of every soul and its journey through time. In modern science, the holographic principle suggests that information about the universe is encoded on its boundary, raising the possibility that the cosmos retains a record of its own evolution. And if the signals we detected are intentional, it suggests we are not alone, that there is intelligence out there, perhaps watching us, perhaps waiting for us to make contact. The search for extraterrestrial intelligence, SETI, has been ongoing since the 1960s, with projects such as the Allen Telescope Array and the Breakthrough Listen Initiative scanning the skies for signs of alien civilizations, while no definitive evidence has been found. The ongoing discovery of exoplanets in habitable zones, such as Kepler 442b and Proxima Centauri b, has fueled optimism that life, and perhaps intelligence, exists beyond Earth. The James Webb Space Telescope represents a monumental achievement in human ingenuity. Its sunshield, the size of a tennis court, protects its sensitive instruments from the heat and light of the sun, Earth and Moon, allowing it to operate at temperatures as low as 223 degrees Celsius. This extreme cold is necessary to detect the faint infrared light from distant stars and galaxies, which would otherwise be overwhelmed by the heat of the telescope itself. The sunshield's 5 layers, each thinner than a human hair, are made of kapton, a material that can withstand temperatures ranging from 269 to 400 degrees Celsius. Its 4 scientific instruments, NIRCam, NIRSpec, MIRI, and FGS NIRIS, are designed to capture and analyze light from the earliest stars and galaxies, providing us with a window into the cosmic past. NIRCam, the near-infrared camera, is equipped with coronagraphs that block the light of bright stars, allowing astronomers to observe faint objects such as exoplanets orbiting them. NIRSpec, the near-infrared spectrograph, can simultaneously observe up to 100 objects, breaking down their light into spectra to reveal their chemical compositions and physical properties. MIRI, the mid-infrared instrument, is capable of imaging and spectroscopy in the mid-infrared range, enabling the study of distant galaxies, newly formed stars, and the atmospheres of exoplanets. FGS NIRIS combines a fine guidance sensor for precise pointing of the telescope, with a near-infrared imager and slitless spectrograph for wide-field imaging and the study of exoplanet atmospheres, as it continues its mission, orbiting the Sun at the second Lagrange point, 1.5 million kilometers from Earth. We stand on the precipice of a new era of cosmic exploration, an era that will test our courage, our creativity, and our capacity to wonder. As we step through that door, we take a giant leap towards understanding our place in the cosmos. We may not know what lies beyond that veil, but we are certainly excited to find out. For in the end, the universe may not be a random expanse of chaos, but a tapestry woven with order, symmetry, and intelligence. The idea of a cosmic tapestry has been explored in various cultural and artistic traditions. In Islamic art, intricate geometric patterns symbolize the interconnectedness of all things and the underlying order of the universe. In Native American mythology, the spider grandmother is a creator figure who weaves the web of life, connecting all living beings. In modern science, the cosmic web refers to the large-scale structure of the universe, a filamentary network of galaxies and dark matter that spans billions of light years. And if that is true, then the next image from James Webb might not show us where we came from, but where we're meant to go. The stars may never look the same again. They may instead appear as guides, markers on a cosmic map leading us towards a future where we are not just observers, but active participants. In the grand narrative of the universe, the notion of stars as guides has been central to human navigation and storytelling for millennia. Ancient Polynesian navigators used the stars to traverse vast oceans, while the constellations of the night sky have inspired myths and legends in cultures around the world. In modern times, the stars continue to guide us, both literally, through GPS satellites, and metaphorically as symbols of aspiration and exploration. The journey of discovery is far from over. In fact, it is just beginning. With each new image, each new data set, the James Webb Space Telescope brings us closer to unraveling the mysteries of the universe. And as we do, we come to realize that the universe is not just a collection of stars and galaxies, but a living, breathing entity, a cosmic ecosystem of which we are an integral part. The idea of the universe as a living entity has been explored in various philosophical and scientific contexts. In the Gaia hypothesis proposed by James Lovelock, the Earth is viewed as a self-regulating system that maintains conditions suitable for life. Extending this concept to the cosmos, some scientists have proposed the idea of a cosmic Gaia, where the universe itself exhibits properties of self-organization and emergent complexity. The future of cosmic exploration is bright, and the James Webb Space Telescope is our torchbearer, lighting the way as we venture forth into the unknown. As we continue to push the boundaries of our knowledge, we are reminded of the words of astronomer Carl Sagan. Somewhere, something incredible is waiting to be known. With the James Webb Space Telescope leading the way, that incredible something may be closer than we think.